Now the fish is pushing against water. Remember, and the water pushes back in an equal and opposite force, and so we get a component of that that pushes the animal in the forward direction. For the snake, it can't push against the air, right? It's just not going to work. You're not going to be able to exert sufficient force against the air and the air back against you to push you forward. So instead, what that animal's doing when it wraps itself into these curves is it's pushing against irregularities in the environment. A rock, a stick, something along those lines. Oh, the reason I kept on so this is just handout 34, but it's showing you something that's very, very close to what we were talking about with the fish. In other words, you have this big dark thing, that's your irregularity in the environment. And the snake then is pushing against that. You have an equal and an opposite force. You can resolve that into two components, a lateral component and a forward component. And it's that forward component then that allows the animal to move in a forward direction. In actuality, the number of pivot points or things that the snake is pushing against, it's actually better to have fewer than it is to have many. So this is showing with 3, 4, and then multiple different places in which that snake can push against. And this was just in the laboratory, and these were all force transducers, and so you can measure the strength of the force, the magnitude of it, and also the overall direction of the force. And you can see what happens is when you get up to C with the many different pivot points, we're getting a lot of lateral motion. So 24 units of force, 26 units of force, there was a balancing out, and only 22 forward. But if you look over here at B, you have 12 to the left, 13 to the right, and 18 forward. So this would be more efficient than this would be because you're using less of your energy, wasting less of it in your lateral movement than you would be in something like this right here. So you're better off with fewer pivot points than many, many different pivot points. All right, so these animals are sliding over the ground, pushing against obstacles. Because they are sliding over the ground, they tend to have large, very smooth scales on the ventral surface. And that's going to help minimize the amount of drag, minimize the friction with the environment. It's a very common mode of locomotion, but it can't be used everywhere. It's not very good in a straight tunnel, for example. Not very good on very smooth surfaces. And it wouldn't be very good on something round and thin, like a tree branch. So we do have other ways in which snakes can move. Concertina. This is used by all when they are on flat surfaces without sufficient pivot points. So if we put a snake on the floor in here, there's a high likelihood that it would start using concertina locomotion because our floor is smooth. There are no bumps, there are no irregularities. So this is illustrating concertina locomotion, 3 different ways in which concertina can be used. This would be the most common for an animal on something like a floor, on a very flat surface. And in these diagrams, what they're showing is by the stippling, the dark dots, they're indicating what part of the snake is in contact with the earth. Right? So not all parts of the animal are in contact as it's moving. So we can go from top to the bottom, for example, and you can see what's happening in the top is the rear portion of the animal is anchored. And the front, what's that, about 60% The front 60% is lifted up and is actually stretching it forward. Right? So the back remains in contact with the earth. The front was curved, the animal lifts up its body and then begins to straighten out those curves. So that you can see what's happening is the head is getting farther forward. Then when it's totally stretched out, the entire animal is in contact. Then it's going to anchor the front region and draw up the rear. Draw up the rear. Draw up the rear so that you are now curved to a certain degree. Then we'll go from having the front anchored back to this again, with having the back anchored and pushing forward and stretching out. So that's the basics of concertina locomotion. When you don't have a lot of irregularities in the environment, movement like this often is possible. Sidewinding. Sidewinding is typical of some snakes in African and American deserts, but many other snakes are capable of using it. So even some of our colubrid snakes, for example, in Michigan, in the dunes along Lake Michigan, would end up using a sidewinding motion. So there's sidewinding. The concept is the same in the diagrams, that you have the part of the animal that's in contact with the earth is indicated by the dark stippling. If it's white, then that is the part of the body that is raised up off the ground. Note that the snake's body is always in two different tracks at the same time. So he's well anchored over here. The front part of the body has been put forward and is making contact. And then we're just following that, and starting it all over again. The snake's head is pointed in that direction, but the actual direction of movement is like that, towards the top of the page. So that in the long run, you would end up with a whole series of those J-shaped tracks in the sand being left by this animal. And it's not dragging anything in between those tracks. It's going up over the sand and making contact, and then pulling the back up and over as well.
Which species did you say sidelined like this?
Well, there are many species that live in the African and American deserts. For example, there is a sidewinder that's a rattlesnake that lives in the American Southwest that typically moves like that. But many other snakes can adopt this type of locomotion in a sandy environment. So colubrids could do it. If we found a milk snake or a blue racer out along the coast of Lake Michigan, it probably would be doing that as well. Rectilinear. Rectilinear is the only one of the four modes of locomotion that does not involve lateral bending. So all the other three involve lateral bending. And so what's going to occur is that muscles on both sides of the animal will contract simultaneously. And if you look at from the side, this is an exaggeration, but that's what would be going on. Essentially inchworm type of movement, but in a snake. So it's going to have multiple folds to its body. It's contracting on both sides, lifting up, stretching forward, anchoring, and then bringing up the rear, bringing up the rear, bringing up the rear. This is typically used by really heavy-bodied snakes, so boas and pythons are always going to be using rectilinear motion, or almost always. Right. Okay, so they lack limbs. They can use them for courtship purposes if they're in the family Boidae. Everybody else does not have them, so they have to accomplish their locomotion in a different way. Most of the time, it's done by having lateral bending of the body, but we can have lateral undulation, concertina, or sidewinding. And only one type of locomotion does not involve the lateral bending. Instead, it's more like an inchworm type of movement. Snakes are different than most other vertebrates too. Not all, but most, in that they have a large amount of craniokinesis. So you often think of a skull as being a very solid structure. All right, the bones are firmly fused to each other. And that's true when you look at mammals, and it's true when you look at amphibians. But it's less so in birds and definitely less so in snakes. And so we have more craniokinesis in snakes than in any other vertebrate. Well, what do we mean by that? Okay, kinesis is just referring to movement, cranial movement. We can have movement between the bones of the skull. That's what craniokinesis is. And we can just look at the bottom diagram. It is somewhat diagrammatic. But the point is that those lines there, okay, these dark striped structures, each one of those is a bone in the skull of the snake. And where they show the little round circles is a place in which you can have movement between those bones of the skull. So they're not firmly fused together. They can move independently of other parts of the skull. You have this in the skull. You also have it in the mandible, so that the front tip of the mandible is not solidly fused. Instead, the left side of the lower jaw and the right side of the lower jaw can move independently. All right, so what's this do? It does a couple of things first thing. One, it gives it a very wide gape. It is able to open its mouth very, very large, right, compared to another animal with a similar type of a head. That allows the snake then to accommodate either large or odd-shaped food. So food that an amphibian of comparable size could not do anything with, a snake is going to be able to swallow it. It can do so because by manipulating the bones of its head and by manipulating the bones of the lower jaw, it can accommodate these large prey items, these large odd-shaped things like a struggling mouse, for example. The jaws, lower jaw, being independent, is also important because it is used in drawing the prey inwards. So snake teeth are recurved, and that just means that they curve backwards. So they're not just straight spikes coming down. They come down and curve back towards the inside of the mouth, towards the throat area. So that when that snake is going to swallow something like a toad or a mouse, it will take those jaws and push them forward and then grab those teeth into the prey. And then it'll push the other side forward, grab those recurved teeth into the prey, and then it essentially is walking that mouse or that toad into the throat of the snake. So we have a combination of recurved teeth, craniokinesis, and the ability to operate our lower jaws independently that allow these animals to manipulate food items and to take in very large and very odd-shaped structures as well. some snakes will have a venom.